two problems that are going to move us toward some understanding of orbital mechanics. First of all, if you have, I'll put this in context now, if you have a satellite in circular orbit, okay, if it's in a circle, then it's got to have a net force equal to mv squared over r. It's the centripetal force, that's the thing that keeps it in the circle. It's up there outside of the atmosphere, nobody's tugging on it. The only thing that's going to provide the force is gravity. And gravity is toward the center of the Earth. Okay. So that the gravitational force has to equal the centripetal force. You, of course, would recognize this as the centripetal force, and this is a gravitational force. So centripetal force equals gravitational force. So you have a very simple equation that everybody solved right, except I think one person might maybe didn't divide out the little m's. Okay. You got a little m here, a little m here, so you're not going to have a little m in your final expression. I think I saw that in somebody's. Everything else was right. Well, everybody's algebra is up to solving this, which is very good. And you get velocities, the square root of big G, big M, little big G, big M over R. For Earth, big G, big M is really pretty close to 4. I got to be careful. 4 times 10 to the, it would be 13th. Well, meters squared per second squared. R. $6,400 kilometers. It must be off by a factor of 10 somewhere. 6.67 times 6 is 40. 10 to the negative 11th, 10 to the 24th gives us 10 to the, oh yeah. I was thinking negative when I should have thought positive. Anyhow, 10 to the 14th. Okay. So if you divide this by this, you're going to get something like 6 times 10 to the 11th, which is like 60 times 10 to the 10th. But that's kilometers, so 60 times 10 to the 7th, 6. The square of 60 is 8. Yeah. You find If you have just a little more in the radius of the Earth, this comes out on the order of 8,000 meters per second, which is about 17,000 miles an hour. Okay? And that's your orbital speed in low Earth orbit. Now, if our 6,400 kilometers, you're not going to orbit for very long. You might be up 20 or 30 miles. You're not going to get a lot of air resistance because the air's pretty thin then. You got to be up at least 100 miles to be able to orbit for a couple of days. And you got to be up a lot higher than that if you want an orbit to last a while. Okay. 100 miles would be about 160 kilometers. So let's just say 6,600 kilometers would give you the velocity of a low Earth orbit. Now, so you see, it's easy to calculate, right? All you got to have is a gravitational constant, the mass of the Earth. And the radius of the orbit. Okay. Okay. For this one, work is the integral of f dot delta s. In other words, if you have a path, straight line path and a constant force, you just take the dot product of the force with the displacement and you get the work, right? And that's equivalent to taking the component of the force in your direction of motion and multiplying it by your distance. But there's the integral definition. So let's write it neatly. Okay. Well, little notation. It follows that the work from point 1 to point 2 would be the integral from R1 to R2 of negative big G big M over R squared dr. I could develop that integral for you, but you want to figure that out. Okay. You're simply integrating the force over some distance, and implicitly we're assuming by dr that you're moving radially away from the Earth, so that you're moving along the same line as gravity is pulling. Okay. I'll just make the note that delta R and force of gravity are both radial when you're setting up this integral. So dr is going to be radial. Gravity is going to be radial, but toward the center of the Earth. I didn't say whether moving toward the center or away from the center. That depends on whether R1 is bigger than R2 or less than R2. But if R1 is less than R2, then we're moving away from the center because R is increasing. Okay. Well, you do that integral.
But all of our other measures are in. So your final answer is yours. What do we do to get?
Antiderivative is, I mean, GM is just a constant that comes out. You're just integrating -1 over R squared, and you get positive GM over R, which you evaluate between R1 and R2. Equals GM over R times 1 over R2 minus 1 over R1.
Divided by 3, it would be. But we could also just reduce that fraction. So instead of
Well, that's pretty straightforward, right?
taking that down.
Just integrating 1 over R squared. So be sure you understand that,
Reduce that fraction down.
because
But
most of you, I don't think, got that. A lot of you knew you had to do an integral. I think everybody knew you had to do an integral. You weren't sure what to integrate. And of course, once you know what to integrate, it's an easy integral. Okay, so my question is, work by gravity. Big M equals big G, big M over R times 1 over R1 minus 1 over R2. Sorry, it's 1 over R2 minus 1 over R1. Okay. R2 is bigger than R1. Is this work positive or negative? Look at it for a minute. Think about it carefully. And then vote. I'll ask you in a minute. Positive or negative. Don't say yet. Okay, how many think it's positive? How many think it's negative? What's bigger, 1 over R1 or 1 over R2?
This case, I square.
Yeah. That confused me too. Okay. The reciprocal of the smaller number is bigger than the reciprocal of the bigger number. So it's negative. Took me a while to get that through my head when I was first learning this stuff. Okay. I believed it, but it just didn't seem natural. It still doesn't even look natural until you stop and think about it a few times. Okay. Okay, well, then the question is, this force is conservative. So is gravitational change of potential energy
And clearing that radius, right?
is it positive or negative when R2 is greater than R1?
putting it all over the place.
You know what? It's okay. In every one of these, I left off the M. Yeah, I divided the M out over here and I forgot about M completely. Try to pay more attention than I do. But we're calculating work and we don't get units of force unless we got that little M over there. I'm just gonna write little MGM. So it seems like a movie studio. Then I'll put the little M on it here.
So
Okay.
78.5 multiplied by.
I'm actually gonna rewrite that top.
So we're looking for-
But now
Yeah,
it's
here.
changing.
So we got
potential
pi r
energy.
squared.
In order to be work, you gotta have little M there. If you don't know what little M is, then you have the work per unit of mass, which is another important quantity, which is called gravitational potential. But I'll come back to that.
Which is.
Okay, so tell me, how many think it's positive? How many think it's negative? Okay, well, 3 out of 4 voted positive and 1 abstained.
Positive.
Go along with growth. Yeah, well, it's probably a pretty thing to do. It's a pretty good crowd here. Okay. Well, you get all that straight. And then how would you find out then the potential energy? From R equals 6,400 kilometers, which we're just taking as the radius of the Earth. So you're on the surface of the Earth. Actually, you might be in a tower about 30 miles high, but you know, just using that ballpark radius of the Earth to an orbit with a circular orbit to a position 7,000 kilometers from the center of the Earth. Let me rewrite this, make it correct. Well, you could do that, couldn't you? Because you know the change in gravitational potential is negative of the work done by the gravity because potential energy change is equal opposite to the work done by the conservative force, right?
So, and that's probably gonna be like.
And that's going to be big G, big M, little m.
Piece of the, or the measurable same, or that bucket, or that.
I hope I wrote it down correctly over here. Okay, just stupid little error here. We're substituting R1 and R2 for R, so we're not going to get an R here.
We also. Rover's gallons, which are not.
We're going to get G, big M, little m times 1 over R2 minus 1 over R1. There's not going to be that R in there. Writing things down because that's what my hand tells me to do.
We end up
So if you do this carefully, you find it's very easy to get from here to here. Get from here to here, okay? So if you're using this a lot, you're going to remember it. If you want to clutter up your brain so that you can't remember anything in the final exam, you memorize this as a formula and confuse it with this maybe. But right there is your universal gravitation, and you just have to integrate that between two r's. It's a simple integral if you don't do the bonehead thing that I did, okay? Simple integral. It gives you this. So you never have to be confused about what these formulas are. So you can, if you've used them enough, you're probably going to remember them, but you can always check them out. You don't put a time limit on you. It doesn't take but 2 minutes to check it out if you're slow. And if you've thought it through, whenever you use this, ask yourself, why does this work again? It goes back to this. Why is there a negative in here? Because gravity is a force of attraction. Okay? Go back to what we saw last time. All right. Well, from 6,400 to 7,000 kilometers, of course, then I'm just going to plug in the 6,400 kilometers here and the 7,000 kilometers here, and you're going to get a positive or a negative change of potential energy. Well, it's going to be positive because 1 over R1 is bigger than 1 over R2. This is R1, this is R2. But R2 is bigger than R1. This fraction is going to be smaller than this fraction. And as you would expect, the same reason when you lift that concrete block, you're doing positive work against gravity because gravity is doing negative work on you. And you're increasing the potential energy of that block. As you know, if you drop it, it's going to fall, and that potential energy change is going to convert to kinetic. Less a little bit for air resistance, but you don't get a lot of air resistance to a concrete block dropping it from 6 feet. Got a question? Okay, so again, the question was, well, when you did the negative there, you just changed positions of these two things. Something like, you know, was R1 here and R2 here, now R2 is here and R1 is there. Okay? Looks like you just kind of switch them, but no, you switch them because you change signs. You distribute a negative through this, you get a negative 1 over R2 and a positive 1 over R1. Well, you choose to write the positive before you write the negative. And then you again have to think, if R2 is bigger than R1, does this make sense? If R2 is bigger than R1, this is a smaller fraction than this is. Got a bigger denominator, okay? So you're going to get a positive. If you're moving from closer to further, if you're moving from 6,400 to 7,000 kilometers, R1 would be the larger, 1 over R1 would be the larger fraction. 1 over R2 would be the smaller fraction. You got to do this a few times and think about it when you're doing it. Just don't blindly plug things into formulas. Think about how they're connected to reality. Okay, everybody's been to space, right? Did you think about this when you're going up? No. Anybody hasn't been? Oh, wait a minute, whoa. I was thinking 300 years in the future. Never mind. Okay. Got it? That's important. It's easy to get confused. And it's just plus and minus signs. It's really easy to get confused. Things don't quite look the way they really are. Okay. Okay, well, what's the kinetic energy?
Talking about solving this problem for volts. Your volt's gonna go into a circular area that is
Let's just say,
theoretically base. That's a, where cutting the mirror, fitting more surface. So hey, say that, it's not always, so it needs to lay out that way, but it never means maybe third of the year. Half, that kind of fit in that kind of ratio of spiral, it also, it makes the progression of their actual too. Anybody ever?
well, your change in kinetic energy is just the kinetic energy.
Here, accommodate,
You know, in other words, you got a rocket sitting on the launch pad, consider it to be at rest in your frame, which of course is on a rotating Earth going around the sun, which is moving around the galaxy, right? But just in the frame where you think the rocket is stationary, which is going to be okay. Not really, because, you know, you want to, Earth rotates, right? So you want to launch in the direction of Earth's rotation, because you pick up to 700 miles an hour by being in the direction of Earth's rotation, as opposed to trying to launch opposite to the direction where you lose 700 miles an hour. Okay. So you want to launch toward the east. Still, no digression there. Let's just assume you're at rest. If you want to give yourself 700 miles an hour, which is about 1150 kilometers per hour, so many meters per second, you can do that. But let's just take the kinetic energy. Let's just assume you're at rest, even though you aren't. Figure out the kinetic energy in the orbit. And can you write the expression for the kinetic energy? In a circular orbit at distance r. Okay, so the kinetic energy, this is basically a particle circling around the Earth. One half mv squared. What's v? Maybe not my m again. 1/2 m squared gm over r. And I'm going to leave the 1/2 in there. 1/2 big G big M little m over r. Now, unfortunately, I'm out of board space here.
Incorrect
How much board can I see? Move the camera just a little.
So, there can be also provides for runoff. So it's very.
Okay, now.
Also mentioned that a lot of especially, spacing, right?
Let me ask you to do another interview. Okay.
specify application rate. Like, pound per thousand square feet. And I think that's the thing that we see a lot, it's pretty cool. Chemical or, huge.
What's a change in U from distance R implicitly from the center of the Earth to the center of a planet? Distance R to infinity. It's from mass little m, vicinity of a planet, big M. Distance R from the center of the planet. Okay, we don't want to take too much time on this. A lot of you write down good stuff. We have this expression for delta U from R1 to R2, right? Well, as R2 gets really big, what happens? This fraction becomes insignificant, right? Okay. And this fraction remains because that's where you start from, right? So you could say it's just going to be big G, big M, little m over R. How does that compare to this? This is half of what that would be, right? So your kinetic energy in a circular orbit is going to be half of the gravitational potential energy relative to infinity. Okay? Well, we can move that out. I'll just do kind of quickly. Work done by gravity is the integral from R to infinity of big G, big M, little m over R dr. And that should be negative. That's a force exerted by gravity over R squared, which is the limit as I'll say I like using it because it usually is the radius of the Earth. As big R goes to infinity, at the integral from little r to big R, taking G big M little m over R squared dr, which equals the limit as big R goes to infinity of big G big M little m over R evaluated little r to big R. Limit as big R goes to infinity of big G big M little m times 1 over big R minus 1 over little r. And as big R goes to infinity, that's just big G big M little m over R. Delta U
diameter, and here's another thing where we're approximating, right? Because
R to infinity is negative big G big M little m over R.
What the size is. So we're trying to approximate the big that our math will work.
So that's really easy, but that's the way you write it out a little more formally. And I'm just starting again with the work done by the conservative force, which is this. That's the work done by gravity. Delta U is equal and opposite to the work done by gravity. Okay.
How that works. All right, so the pots are sold in bundles of 80. So how many bundles of pots?
And I got negative signs messed up. This should be negative big G, big M, little m over R. This should be positive big G, big M, little m over R. Except that's not right. It's gotta be negative. No, never mind. So my next step is take infinity is a reference point. For u, i.e. u equals 0 at r equals infinity.
Why don't we just talk through that real quick? How would you react? Theoretically.
Right this way, since delta u r to infinity is big G, big M, little m over R.
Well, area always.
Delta u from infinity to R is negative big G, big M, little m over R. Now again, this whole thing with positives and negatives, it'll flummox the heck out of you. We're saying that the potential energy then in any Earth orbit is negative. But it's negative, and as you move away from the Earth, it gets less negative. So as R increases, your potential energy increases. Okay. The only place that makes any sense for a reference point for potential energy, whether it be Earth orbits or atomic orbitals, okay, is infinite separation. So that U bars, yes.
So that's pretty simple. It's really as simple. Are they truly similar? Often they're something more like this.
It's negative, but it's increasing as R increases.
So that case, you might have a little bit more complicated. I would get really what I would do in that case. So look at an area of.
Why? Because as R increases, 1 over R decreases.
So anyway, yeah, that's, you want to make sure that that measure is correct. Frequently when you're buying pots.
It's confusing, but it's worth sorting out. Many things you're not going to understand very well if you don't get this sorted out. Again, don't expect to sort it out the first time you try. Just keep thinking through. Okay, well, in any case, in a circular orbit, then It'll be a planet of mass little m. My n looks like an M, so IN in circular orbit.
Got a little side for that.
So here's your kinetic energy, here's your potential energy. What's the total energy of your satellite?
So we have one more conditioner, pointer.
Now, you should be very aware, and most of you had to stop and think a little bit, but a lot of you got the right thing in the leg, just did your arithmetic wrong. But talk about the total mechanical energy. Okay, you should know total mechanical energy is kinetic plus potential. So it should have taken you less than 2 seconds to say, well, that's potential plus kinetic, or kinetic plus potential, in the order I wrote it, but okay. And that's 1/2 big G big M little m over R minus big G big M little m over R, which is big G big M little m over R. It's going to factor it out times 1/2 minus 1, right? Which equals negative 1/2 big G big M little m over R. So you've got negative total energy. Well, that's okay, because you can put your reference point for potential energy out there at infinity, which means just about every energy in the universe is negative. Okay. Well, that's an exaggeration, yeah, particles and stuff, but the potential energy is negative, but the potential energy at the surface of the Earth, where R is less than it is at the orbit, is greater than this, okay? Because R is less. And again, you just kind of got to sort the whole thing out, and you got to start with the idea that everything in the universe is at a gravitational potential energy hole. We're all of us are in a hole relative to infinity, because it would take a lot of energy to get us out to infinity. Okay. Now, another question, how much energy take us to get out to infinity? Well, from distance R, this much.
How would you obtain information?
Give a satellite this much energy, and it's never coming back.
And the simplest way, divide seeds into.
If you give it this much energy, then you set 1/2 mv squared equal to this, and solve for V.
So just saying it.
And you get the square root of 2G big M little m over R, which compares to that square root of big G big M little m over R, having a 2. So I can also tell you that somewhere here, one more thing. To get from R to infinity, requires energy, big M, big G, big M, little m over r. Okay?
Mary farms and they're tracking their strawberry production. You're going to use that analyzed data to generate what our estimated fields. Then they're probably also going to have.
So kinetic energy is 1/2 mv squared. If you start with more energy than you need to get there, then all the way gravity is going to be sucking energy. Okay? But you're going to have enough to overcome that potential energy change. Your potential energy is going to go up by this much, so you better have this much kinetic energy. You got to overcome this much potential energy change, which we calculated all the way over here. I've got it off the board now, but it's there at the left-hand side of the board. So that tells us velocity has to be greater than 2 big G big M little m over r. Compare that with the kinetic energy for circular orbit. So to get away, we only have to reach a velocity that's the square root of 2 times orbital velocity.
Sometimes we could look at it in terms of.
And I said compare kinetic energy for circular orbit. I mean, compare velocity v for circular orbit. Okay. Again, I'm being careless. I'm implicitly letting r be the radius of the Earth. Well, no, never mind. There. Okay. So this is your escape velocity. If you're in an orbit at radius r, that's how much velocity you got to get to escape Earth's gravity. If you're on the surface of the Earth, then r is going to be your 6,348 kilometers or whatever it happens to be. Okay, the radius of the Earth. Escape velocity from the Earth, r equals radius of the Earth. So that can all be summarized, but you've got it all. And I'm going to recommend that you summarize it. What do you know about a circular orbit? Well, you know that the kinetic energy is 1/2 big G big M little m over r. You know that the potential energy is negative big G big M little m over r. A lot of the same expressions connected by what should be fairly obvious calculations. At least they should be fairly obvious by the time you work through these things. Okay. Now, I prefer when we're doing gravitation to do a lot more with orbits than your textbook does. Okay. I don't disagree with your textbook's emphasis, but I wish they would have enhanced it a little bit more with this stuff, because it's more direct. They tend to go to Kepler's laws and stuff like that, which is all great stuff. I'm going to emphasize this. and I'll be sending out some problems, maybe not till tomorrow afternoon. But I'm gonna make the problem, because your book has a problem. Okay, when I was looking through, so I said, wait. Where's all this stuff on circular orbits? Okay, well, there's a little bit more. And you see that in working this stuff out, one reason I really like to do it is that it kind of helps you focus everything you've been learning up to this point about energy.
Some of our overhead balls needs
Okay.
lower than
About
our
circular motion, centrifugal force, brings a lot of stuff together. And toward the end of the semester, that's what we're trying to do. So there's more stuff, of course, that this brings together. I think I've got, yeah, I've got some more back there. Okay. Okay, so let's say you're in a circular orbit. I'll just put a big M there for the mass of a big object and a little m out here. And it's all lopsided, but it's supposed to be circular, okay? What happens if you're at this point and you happen to be pointed ahead in your circular orbit and you press on the gas pedal? Actually, you burn some fuel in your rocket thrusters, right? And you speed up. What happens when you speed up? Well, when you speed up, you put an impulse F delta T. That's what this vector is. What's that do? Well, that tends to move you into a bigger orbit. Okay? But that bigger orbit is not a circular orbit. It'll go around here, it's going to come back here. And even a bigger orbit. Okay, now it's not going to come back to exactly the same spot here. You go from a circular orbit to an elliptical orbit. And that's a badly drawn ellipse, but you get the idea. Okay, so let's say here now you got, I'm just going to represent the big mass big M as a point and try to draw a little better ellipse. Still not a great ellipse. In any case, the ellipse has a major axis. Perihelion is your closest approach to the mass big M. I don't know if that's pronounced aphelion or aphelion. We could see it either way. I don't remember hearing anybody pronounce it. At least not when I was paying attention. Okay, so you look up the proper pronunciation and share it with me so that after all these years, I'll know how to pronounce that word. I could put it into search engine to tell me. I've never actually thought to do that at a time when I wasn't thinking about something else. Okay, so in here you got perihelion and aphelion. Okay. What's happening to the angular momentum of this mass about the relative to the center of the planet? Well, what is it that changes angular momentum? It's torque. Okay. You need a torque to change your angular momentum. How much torque does this thing get? Let's say the satellite is at this point. Okay. Can you draw me that picture and draw your R vector? And draw your force vector. Remember, this is your reference point, so the R vector goes from here to there. What, and where's your force vector? Draw those two vectors and label them R and F. That's a work in progress. It takes a while. Okay, well, what's our R vector? Our R vector, I said that our point of reference is center of the planet. So our vector goes from the center of the planet up to our mass. Now, where's our force vector? In what direction is the force on our mass? Well, it's a gravitational force, right? What's the direction of the gravitational force at this point? Back toward the planet.
Especially in controlled environment agriculture where might have carbon dioxide reaction.
There's F. Tell me.
Very important because high levels of carbon dioxide are time for talking about that. All right, well.
What's R cross F?
Oil application problem. So our objective here at freezing solution, you can concentrate the oil product.
If you try to use your right hand, you're going to be in trouble. You can't turn one vector toward the other. There. Well, you can. But if you do, you turn them 180 degrees, and the cross product is zero. Cross product of parallel vectors is zero. Cross product has magnitude equal to the magnitude of R times the magnitude of F times the sine of the angle. What's the sine of the angle between these? Angle between them is 180 degrees. What's the sine of 180 degrees? Zero. Okay. So that the R cross F is just a zero vector. How much is it going to change the angular momentum over the next couple of seconds? It's not. Zero torque, because this is the net torque. Oh, wait a minute, I don't want to say that. Yeah, I do.
Yeah, 8 trees. So, which often we'll see that with emphasize.
No, I don't, because that's gonna get confusing, because I keeps changing. Okay,
So, okay. In this, good business. No.
what I was writing there, what I was starting to write was, ignorant,
Thinking about.
incorrect. Just gonna say, tells you that your angular momentum is constant. Okay? You don't have a net torque, you're not going to change your angular momentum. Now, there are other implications of that, but we're out of time, so people probably need to go to work.
Yeah.
One consequence of this is your speed at aphelion is in a ratio of your speed of perihelion inverse to these two distances. The speeds at these points are inversely proportional to the distances of these 2 points from the center. So you're going a lot faster here. I don't know if you've been reading about that mysterious comet that just went past the sun, but it just reached its perihelion a couple of weeks ago. And it's just now kind of emerging out of the glare of the sun, and it's doing really weird stuff, really interesting. Okay. There's some people think it's alien. Well, it is alien. It's not, it's outside of our solar system. But I don't know if it's intelligent aliens. It's doing weird stuff, but it doesn't seem to be, to most people, to be consistent with alien technology. Okay. It's very interesting. Unfortunately, when it went past the sun, we were out here, so we couldn't see it. But our Mars probe was over here someplace, so it could see it. So it sent back some pictures. It's pretty neat stuff. But we are out of time. And we'll see a little bit more of this, but I'll work it into the problem. Thank you.